Hi everyone. Today I'm going to show you how to generate bridge rating curves using HEC-RAS software. Please note that this video may not be a proper guide for the professional users of HEC-RAS. It is for the modelers who have minimum or even zero knowledge of working with HEC-RAS, but they need to generate bridge rating curves since there are some softwares like ICPR or SWMM that they can't directly model bridge, but they support family rating curves. So in this video, I'm going to show you how to generate or how to set up HEC-RAS and generate bridge rating curves and transfer them into ICPR model. My video is split into two sections. First, I'm going to talk about the fundamental of bridge. And in the second section, I will explain generating bridge rating curve. It's good to know that sometimes if you're using cross-section data from another software and to HEC-RAS, there are some model that cross-section structures are different than in HEC-RAS. For example, this cross-section left side is from ICPR 4. You can see the graph. Both sides shows everything is the same. Manning value for overbank for both models or for both HEC-RAS and ICPR is 0.15, and then main channel is 0.045, the Manning value, I mean. But if you look at the input data in Manning value for station 0 is 0.45, while you have 0.15 in HEC-RAS. And the reason is that in ICPR, the first Manning value is dummy, and then the second station from station 0 to station 25, the model uses the Manning value of 0.15. But in HEC-RAS is different. The first Manning value is important. From station 0 to wherever you have the second Manning value, the model uses 0.15. So if you use exact data set from ICPR to HEC-RAS, then these two cross-section would not be identical, and there is a problem. So we need to make sure that's correct. Here is the schematic of bridge in HEC-RAS. As you can see, HEC-RAS has the features for pile, for bridge deck, for abutment, left side and right side, and it's very handy tool or model for simulating bridge. One thing that I need to mention is in HEC-RAS, the term of pile is not being used. Instead of that, we have pier, and the reason is that in HEC-RAS, if you have one pile, the model use that pile from upstream face of the bridge to downstream, and the model think that's a solid pile. So it is kind of a series of pile from upstream to downstream, which they call it pier. If you're not familiar with family rating curve, here I will explain how to rate that. For family rating curve, the one that HEC-RAS has, your horizontal axis is flow, and your vertical axis is both upstream and downstream flooded stage. Let's assume your downstream flooded stage is 60, and your upstream is 60.5. First, we read 60 is here. We need to go forward from 60 and then get to elevation 60.5, which if you read this, 60.5 is here. So wherever we got to point that we have 60.5 here, then we need to read the horizontal axis, which is flow, and then it is about 3000 CFS. When you have flow coming from top to bottom, there is a theoretical location that the full conveyance start to limit or contract to get to the opening of the bridge. The conveyance is not going all the way to the upstream face of the bridge. It stops somewhere and it starts contracting and starts contracting to get to the opening of the bridge. And then from here, the flow start to expand and then get to where that we have the full conveyance or full valley flow. So that's where we have a station. I named it station 4 and station 1. And then when we get here, this is the most restricted area. So it is very important to estimate the lengths of transition upstream of the bridge, where we call it length of contraction, and then the length for downstream, where we call it length of expansion. And then this is exactly the way that we need to set up a HEC-RAS model. We need 4 cross-section of 4, which is full flow or full valley, and then the cross-section 3, which shows the opening of the bridge. This is still full valley, but we need to limit this by an effective flow area. Same thing for cross-section 2. We need to limit this too. And then cross-section 1, which is again the full valley or full conveyance without any limitation caused by the bridge. So if we know the average length of restriction by bridge, we can estimate this length by the reference by the ratio that different reference introduce. Different values are suggested for ratio of contraction and ratio of expansion in different references, but most of the references suggest 1 for ratio of contraction, sometimes less than this, and then 2 for length of expansion. But sometimes you need to experience, sometimes using these 2 values give you very exaggerated or big value for these 2 transition lengths, especially when your average restriction length is big. So that will give you a very big value. But again, you need to experience to see which value works better for your case. As I mentioned, cross-section 3 and 2. So if you go back, we have cross-section 3, cross-section 2. This should be limited, the opening of the bridge. So in HEC-RAS, you have a tool that you can add an effective flow area for this. So you need to make sure that in this ineffective flow area covers your cross section to the top of the bridge. To estimate the length of average length of restriction, normally I add the upstream and downstream cross section in one Excel sheet, and this is the green line is the opening of the bridge. If you know your estimated flood stage, then you know what is really the length for right overbank and left overbank, the length of restriction caused by your bridge. So here you can see the same left overbank and right overbank restriction. But sometimes you have, this is the floodplain. Not all this blue area is effective flow. I assume this is the main, the effective flow area. So that's the way that we need to estimate the length of restriction for left overbank and right overbank. And we need the average of this to estimate the length of contraction expansion, as I mentioned in my previous slide. The last thing that I need to mention here is when you generate bridge rating curve in HEC-RAS using this structure, your rating curves cover the loss through the bridge. So it doesn't have this transition length or this one or length of contraction and expansion. So when you have your bridge rating curve in your secondary software, you need to make sure that you set up these 2 cross section, including the ineffective area for cross section 3, and the same thing here, and your bridge rating curve. If you're not using that, then you're missing this part. Okay, now I want to explain step by step to how to set up a very simple HEC-RAS model to generate the rating curve. First thing is we need to open the software. This is the latest version of HEC-RAS 5.0.7, but the older versions are almost the same, so there is no big change. So if you're using older version of HEC-RAS, it doesn't matter. So first thing that I'm going to do is save this file, save my project, and change the location. We'll call it test. So then we need to set up the geometry data, cross-section, bridge, geometry data, everything. So we need to click on this icon so that will show any cross-section, any data that we have, any geometry data we can see here if you have any. Again, because this data is different than the main project, we need to save the geometry data as well. So I will save this one. The location by default is the same location that your main project is. So I will just give a name, Geo Bridge. So save this one. So right now I have a empty template for geometry data. First step would be the river. So we need to have river, and then we can add cross section. This is a schematic, so there is no coordinate system. It shows here, but we can just draw from top to down or left to right. So it doesn't matter since it is schematic. So start from first point and then double click to end up here. Then you need to have river name and then reach name. So sometimes you have one river and different reach. So you can have this. For this one, because it's just for bridge rating care, we call it bridge, but you can have different name for this. Okay, so we'll close it. So it gives you the river name and then the branch name, which both of them are the same. Then we need to have our cross-section. So click here. That will open up the cross-section data set. So for now, we don't have anything. We need to add one by one our cross-section. I will start from very upstream. If you remember the presentation, it was cross-section number 4. So click here and then add cross-section. So that is very important. The cross-section name should be a value. It cannot be any alphabet or any other thing rather than the number. That's first thing. And the second thing is these numbers should be sequential. So from very downstream you have the lower value, and then each value higher than that, the model set it for upstream. So most of the time, the naming that in different model people are using is the real stationing of the cross sections. For this one, I'm just following what we have in our presentation. So I named this one cross section 4. So that would be very upstream, or a start of our transition from the full conveyance to the opening of the bridge. So I will call it 4. So it generate here. If you look at here it shows whatever cross section that we have. So one thing before copying the data here is if you use the default, so you have station elevation, then the manning value, you have a place for left over bank manning value, right over bank, the main channel and right over bank. So you have 3 value. But if you have more than 3 value for the cross sections, so then you need to use a column here. So we can come here from option, we can click this, So then you have station, elevation, and manning value. So here is free. So then you don't no longer there's option for this part. Normally I use this because I use we have varied value. We have more than 3 values for manning. So I already have data in my Excel sheet for cross section 4. I just copy this one for paste. You click on this and then click shift and then click on this one. So it's select and then Control V will paste the data here. And then if you click on, so here is the graphic view. For now, it doesn't show anything. If you click this, that will show you the data. So this is the links between this cross section to the downstream cross section. For now, just leave it as is. I want to first start with the station. So this is leftover bank station and right over bank station. Just assume this is the main channel and then it's left and then it's right. So I just if I click here, that will jump to this location, but I want to start my manning value for leftover bank with 0.15, since it is very shallower, and then this is we need to look at the aerial map, but just assume we are using 0.15 here. If I click here, it jumps to this location, so I'm going to use 0.045 for this one, and then just think this is my leftover bank station. So I copy this and then paste it here. So I have my leftover bank station. And then for this side, just assume this is my right over bank station. I can do the same thing, copy this one and then paste it here. And then again, this is where I have manning value change again to 0.15. And then if you click here, that shows leftover bank and right over bank stations. So lots of people ask me to how you set up this. So we need to look at our aerial map. We need to know our land use, and then sometime even here is as smooth as your main channel is still you're using a bigger value because here you have shallower flow. Not always, but most of the time. So you have when you have shallower flow, your manning value should be bigger. So that's why I'm using the bigger values here. This is just example. So the last thing, I mean, the other thing that you need to fill out is the distance between this cross section and downstream cross section. If you remember the presentation, that was between cross section 4 and 3. And it was the transition of lengths of contraction. I normally set up a graph here and then set up the opening of the bridge and then max stage that I expect, and then the estimate the left lengths of restriction, left restriction and right restriction here, and then set up a small Excel sheet and then estimate this. So if you remember, that is lengths of contraction, lengths of expansion, and then this is left restriction and right restriction, and then average restriction is the average of these two, which is 227 for our case. And then if we are using this, the suggested ratio for lengths of contraction, that is a one time of this, which is 227. And then for lengths of expansion, it is 454, which is double of this. But as you're seeing here is a very big, I've read lots of references that they say that this is very exaggerating the lengths of contraction expansion. So sometimes I'm using, it depends case by case, but sometimes I'm using 0.5 and then 1.5 or even sometimes 1 for these two values. So that lowers this to 114 and 341. Just assume I'm staying with these two values. So let's go back to our data. for between cross section 4 and cross section 3, we had length of contraction, which is 114. So I use 114 here. You can even copy and then paste. Okay, so that's filled. The last thing that is left here is the contraction and expansion coefficients. HEC-RAS used this coefficient, the downstream value for this cross section between, the lengths between 4 and 3. So this value is not being used between cross section 3 and 4. Most of the time, 0.1 and 0.3 is enough for most of the cross section, unless you have an abrupt change. So since we are not modeling the upstream, the cross section upstream of cross section 4, so that's not important. I just leave it as is. Okay, then we need to go to cross section 3. So I will generate a new cross section, name it cross section 3 here. Again, I will add one column here if I want to, in case if I want to use more than 3 Manning values. Again, I have this cross section 3. This is upstream face of the bridge. I will copy this and then select this and then paste it here and apply this. And then again, for Manning value, I will use 0.15 for leftover bank. And then when we get to bank station, which I assume to be here, we use 0.045, for example. So again, we can use this as left station, bank station, and then this for right bank station. I can copy and then paste, and then I can use this as my changing Manning value to 0.15. So if I apply this, that shows both Manning value and then bank station left and right bank stations. Okay, this is cross section 3. So from cross section 3, we have bridge, and then we have cross section 2. But one thing is important, that we need to leave some space for 12 embankment for upstream face of the bridge and cross section 3, and then downstream face of the bridge and cross section 2. So in my Excel sheet, I have the bridge width 49. For my example, I'm going to use the 5 feet for upstream and 5 feet for downstream. That should be sometimes it is small, but for our example, I'm using this. So from cross section 3 to cross section 2, I need to use 59, 5 feet for upstream and 5 feet for downstream, plus the bridge width. So 59 is what I'm going to use for distance between cross section 3 and 2. The contraction and expansion loss coefficient, this one is important because from whatever we have here, the model use for the distance between cross section 4 and 3, so that there is a abrupt change, because we need to even give an effective flow area. So that's a big change. I will increase it, bump it to 0.3 and 0.5. Okay, so now I need to limit this cross section, since this is this should have just opening up the bridge, and then we need to make an effective flow area for this cross section to avoid the full conveyance happen here. So in HEC-RAS, we have an option of an effective flow area. You need to go to option and then add an effective flow area. For left side, I'm going to use somewhere close to 75 as opening of the bridge. So you need to have the bridge data to come up with this value. And then I assume my top of the bridge is 64. And then this option is when you have a ineffective flow area, you can set the option that when the flood stage get to this value, then it makes the model makes it effective. But since we don't want that happen, we just check this one. Then this is always an ineffective flow area. Doesn't matter if it's over top or not. For right over bank, I'm going to use 120 as the starting of an effective flow area, and then same thing 64, and then check mark, and then sorry. So I did set this one. Not sure why it's not showing. Okay, so you have your ineffective flow area here. Now everything is set up for cross section 3. I need to jump to cross section 2, which is downstream of this. Since for my case, I assume the section for upstream face of the bridge and downstream for face of the bridge stay the same, then I can just copy this. So I can go here and then copy the current cross section and name it cross section 2. Okay, so then everything is copied, but we need to make sure to adjust something, because from here is the distance between this cross section and downstream cross section, which is cross section 1. So the distance between cross section 2 and cross section 1 is the length of expansion. I need to go back and see what was that. The length of expansion here was 341. So I need to change this one to 341 and copy this one for all of this. And then the other thing is the same for contraction and expansion. I believe we need to change it to lower value, because there is no big change between upstream and downstream cross section. But for being conservative, I've seen different reference, they are using bigger value for this one, since this is inside the bridge. I try to follow them, and then I keep this one a bigger value than normal cross section. So now I need to jump on cross section 1. So add another cross section and name it cross section 1. Again, I will add 3 columns in case we have more than 3 Manning value. I have cross section 1 here. I can just copy it and then select station and elevation and Ctrl V, paste it. Apply this. Just assume this is, let me start with Manning value of 0.15, and then jump to my leftover bank station. I will use 0.045 Manning value for main channel. I can copy this one as my leftover bank station, and then assume this is my right over bank station. I'm going to change my Manning value again to 0.15, and then copy this as my right over bank station and apply this. Again, Manning, the contraction expansion loss coefficients are because this is the transition between open up the bridge and then downstream cross section, which is full flow conveyance or full valley. So still there is a big change there. I make it 0.3 and 0.5. And for the distance between this crossing and downstream, since we don't have any cross section downstream of cross section 1, I can leave it blank. The model is not going to be, is not use this value at all. So if I close this, I believe my cross section data is set. So everything is done here. Now I need to go move on bridge data. The bridge located between cross section 3 and 2. I need to name the, add my bridge data and then name it 2.5 or any value between 3 and 2. So then the model automatically place it inside these two cross sections. So bridge data is here. We can generate, when we click this, that will open the empty bridge there, since there is no bridge here. I can go here and then add a bridge and then name it 2.5. If this value is between, since this value is between 2 and 3, if I click this one, the model automatically place my bridge between these two cross sections and show those cross sections 3 and 2 here. Sometime it happens that underneath of the bridge, your section is different. Sometimes you have a modified section for the opening underneath of the bridge. So for those cases, you can come here, and then from internal bridge cross section, you can change this cross section, delete this, which is copied from upstream and downstream cross section. You can delete all of this and then copy the cross section data you have. For our case, I just assume our cross section underneath of the bridge, it stays the same, so it's not changing. Okay, then we need to go and start adding our bridge features. That is for deck information. First thing that we need to fill here is the distance between upstream face of the bridge and upstream cross section. If you remember, I left 5 feet for toe of embankment between upstream face of the bridge and upstream cross section. So I will leave 5 here, and then bridge width, it was 49. Okay, then we have wear coefficient. That is when we have overtopping. If our bridge, top of the bridge is concrete or asphalt, we can use 2.8. If it is earth or open space, we can use lower 2.6 or even lower value. Then we need to fill out the deck data. Just assume we have from station 0 to station all the way to station 200. We have same thing for low chord and high chord data. Assume our high chord is 64 for the entire bridge length, and then our low chord is, you can use 62 and 62. And then here is, this was for upstream, and then for downstream, if it stays the same, we can just click here and then copy this. And then if you okay, that will add our high chord and low chord of the bridge. Let's go back to here. I want to explain one other thing here. This is minimum wear flow elevation. If you add the top of the bridge 64, if you leave it blank, the model use 64 automatically to set up the minimum wear flow elevation. But there is the cases that people are interested to set another link for overtopping. They need to know how much flow is going through the bridge and then how much overtopping we have. Especially when you're using the secondary software, you can generate, you can increase this minimum elevation, so the generated rating curve doesn't cover overtopping. So whatever you have is the flow through the bridge. So for that case, we can add a value of, for example, 80. Elevation 80, which we don't expect that to happen. So your flow curve, your family rating curve is covers just flow through the bridge. Let's leave this one blank and then stay with the case that our rating curve covers both overtopping and flow through the bridge. Okay. Next thing that we can add is the abutment. We can have vertical wall or slope wall, left side and right side. We can, for this, we can assume from station 0 to station 75, which is the opening of the bridge. You have a vertical wall of all the way it goes to 62, and then 62, which is low chord of the bridge. You can use even 63. It doesn't matter if it goes inside the bridge. And then if that stays the same from upstream to downstream, we can just copy this and then click OK. So that will add your left abutment. So now we need to add a right abutment. You can just click add. So that will add your abutment. This time I will assume we have a vertical from wall from station 120, which is somewhere close to this one, and then all the way to the end of the bridge length, which is 200. I have same thing. So 62, 62. That means that you have a vertical wall here. And then if this is the same for upstream and downstream, you can just copy it, and then you add this, then you have a vertical wall for your right-of-way bank. So your bridge opening is almost ready. You can add pier or pile. So just click here, and then most of the time we have pile with one thickness, and then on top of the pile you have a cap underneath of the bridge low chord. So we have varied pile width. So we can start. This is the first one is pile width. Let's go from here. First, you need to set up the center line of your pile, and then I assume for station my pile located at the station 100. So I will add 100 here, upstream and down. It can be varied from upstream to downstream, or it can stay the same. So 100, I use the same center line for upstream and downstream. Then we need to add our pier width. So I would use 2 feet from bottom, from somewhere elevation, for example, 58, all the way to elevation 61, when I still use the width of 2 feet. And then from 61 to 62, I'm going to change my pile width to 3 feet. Okay, and then use the same thing downstream. So if you click, that will generate your pile. So you have a pile with varied width. So your bridge data is almost ready. The last thing is left is your step parameters. That is for the number of curves that model generate. If you're using the less curve, it gives you, the model will be faster, but since we are setting up a very simple model, including just one 4 cross section, 1 bridge, we can use the maximum. If you're using the maximum curves, the positive is that the distance between 2 curves is not a lot, so the model doesn't need to interpolate, because if you have a value between 2 curves, your secondary model need to interpolate. So using the higher volume of curves is, for our cases, is a good thing. So I will use 100 for flow curve And then for submerge, and then when you stay on top of each column, each cell, it shows you the range. So I will use 60 for submerge, and then same thing here. I can use it 50, which is maximum. So 160 and 50. Okay, this is headwater maximum elevation. If you, whatever elevation you leave here, the model generate rating curve up to this elevation. So we need to make sure that this elevation is as the bigger, the highest elevation that we expect. Normally I use a little bit higher than that. That would be a little bit when the model goes high, very higher elevation. The good thing is that the bigger value is better than the lower value. When your value is lower and then you are using your rating curve in another software, that software try to extrapolate, and lots of time it causes instability. So if I expect my flood stage, for example, for 500 years is 67, I will use even 70 here. So that value never going to be used by my model, but I'm in safe elevation. And then we need to set up our maximum flow. I know that for first round, you don't have any expectation for your flow, but you can pick a very big value and then run your model and then see what is the range of your flow and then adjust this. Since I'm using very big value, if I expect, for example, 500 CFS, I will use a couple of thousand to avoid extrapolation or to get something close to this value. So I will, for example, for our case, I will use 5,000 CFS because right now I have no expectation what will happen, but the first time that model generate the rating curve, it gives you some idea about this. Okay, so now you're good. Your data is set. You can see the schematic of your cross sections and bridge data. You can save this one, and then you can go to run on a steady state, and then check the geometry process. This is the only thing that we need to generate our rating curve. Normally it takes very short time, less than 1 minute. It's not a big time, since it's a very simple model. Meanwhile, I can open my ICPR model because I want to transfer my HEC-RAS rating curve inside my ICPR or my secondary model. Okay, it's done. We can close this, and then we need to go back to our geometry data and to our bridge data, and then your rating curve data is saved here. If you look at this, you can see your rating curve data. And if you remember, we used elevation 70, and then we were using 5,000. I was using 5,000, but normally that area never happens. So we are in safe area, maximum to 66 or 67, which is here. I'm seeing some kind of problematic something, but this is not our focus right now. I just want to generate and then send the data in my secondary software. To do that, we need to go to full table data. I can select this and then Control C. That will save all data here. You can paste this data in Excel and then arrange your data the way that your secondary software need. For ICPR, the good thing is that we can directly import this data into my ICPR. So for this, we need to have a ICPR project first. So since I have the ICPR project, I need to go to hydraulic operation table and the rating curve. When we are here, we can create a rating curve and then name it, for example, bridge. And then if you change, because we have different rating curve, we can change it to family of rating curve or family of curves. Then HEC-RAS option appears here. You can just click this and then that pastes all the data that we had there. So you can see the data here. So everything is ready in ICPR. Sometimes we need to run our ICPR model to make sure there is no instability, since I'm seeing some kind of weird thing here. So we need to make sure our ICPR works well. If that's okay, then we are good. Otherwise, we need to try different value for in our HEC-RAS to fix this. My presentation is done. Hopefully this video helped you. If you have any question, please shoot me an email. You have my email in first page of my presentation. Thank you for watching my video.